Right, so we want the reaction 2, and we've now realised that a bromine has been swapped for this NH2 group. So we've realised it's substitution. Right, so what is going to be substituting? Well, we can either have nucleophilic or electrophilic, can't we? I mean, there's free radical as well, but that's only dealing with alkanes, so I'm not gonna stress myself with that one. So we've either got nucleophilic or electrophilic. So a nucleophile is an electron pair donor. An electrophile is an electron pair acceptor. So if it was electrophilic, we'd have to have some electron density in this thing that we're starting with. We don't. So I'm guessing we've got something positive in that first thing. Little delta positive carbon, delta negative bromine. So nucleophilic substitution. Okay, I know that was a lot of spiel for just kind of 1 mark, but I just want to kind of get to the point of what you need to be looking at. What is changing in your molecule, and that'll kind of help you with the mechanisms. Right, the condition now, the essential condition to ensure that only this amine is being formed. So this amine is a primary amine, okay? It's only got 1 carbon chain attached to that nitrogen. So, oh, hello. Somebody's in the chat, just double checking, doing okay? Oh, cheers, Ruth, sorry. So what we've got here, so we've got a primary amine. So we're only substituting once, basically. The only thing, we're only substituting one in 1 time, okay? We're only actually doing 1 substitution. So to ensure that we only actually do 1 substitution, we need excess of our ammonia. If we had excess of our halogenoalkane, once that ammonia has actually been used up, your halogenoalkane will then go and find something else that has that lone pair, which would be the amine that you've made, and we'd get further substitution. So we'll go on to further substitution a little bit later on in the questions, but until then, yeah, sure, yeah, okay. No worries, yeah. So would sorry, so to ensure that we don't have further substitution, we need excess ammonia in there. Great stuff. Right, okay, so next one. Calculate the mass in grams of this propamine produced from 25.2 grams of bromopropane in reaction 2, assuming we have a 75% yield. And we have to give our answer to the appropriate number of significant figures. Right, okay, so how do we work out percentage yield? For some strange reason, this always seems to kind of get people. So percentage yield is your theoretical yield. So what you should be getting divided, oh sorry, not the way around, I don't know the way around, I'm having a moment. Sorry, the actual yield, in other words, what you have got, divided by your theoretical yield, in other words, what you should be getting. Right, so this is an interesting one because it's actually calculating the mass in grams produced from 25.2 grams, assuming a 75% yield. Okay, so we've already got our percentage yield. So we've actually got this 75% yield, so that is our answer. And we are wanting to work out our actual yield, what we are going to get, okay? So what it's produced from. So this, what I'm going to highlight, this here is what we want to actually work out, calculate the mass in grams of that produced. So we already have the percentage yield, I've already got that down. we need the theoretical yield. So the theoretical yield is what we would get if all of that 25.2 grams of our halogen alkane reacted. So in order to work out how much we should get, I need to work out the moles of my bromopropane. So work out moles. So I need moles for the bromopropane, so CH3, CH2, CH2Br. So that is my mass, 25.2, divided by its MR. So it's MR, 3 carbons plus 7 hydrogens plus bromine. I think I'd get that to be 122.9 when I calculated it out the first time. So I can work out moles of my bromopropane, which should come out to be, where I had you down, written down, which should equal about 0.205 moles. Okay, so this is a 1-to-1 reaction. Okay, 1-to-1. If you kind of look on here, whatever we started with, we're going to make. So it's a 1-to-1 ratio. So my moles of my propanamine is going to be the same, 0.205. So that's going to be my theoretical yield in terms of moles. Now, some of you might have changed that into a mass, which is fine. It would work out fine. What I'm going to do is use this number to work out moles of what I've actually got, and then I'm going to work out the mass afterwards. If you've already changed this into a mass, that is also fine. I'm just going to work it in moles. So I'm working out this actual yield on here. Right, so let's have a look at this then. So, what have I got? So I need to do 75 divided by 100 times 0.205. 75 divided by 100 times 0.205. And it does come out to be 0.154 moles of my propanamine to CH2 and H2. Okay, so I've got my moles of propanamine. It wants a mass, so I just take the moles and multiply it by the MR. And the MR of propanamine is 59. And times those two together. Right, it wants the appropriate significant figures, doesn't it? It's asked for, give your answer in appropriate significant figures. So let's have a look. What have I got in my question? I've got that as a number value and that. Both of them are 3 significant figures, so I need to make sure that my mass is to 3 significant figures. So there you go. Right, hopefully all sorted, and hopefully Brendan's now on our little chat as well. So there's Brendan on the chat now, so Ruth said she was there before. Cool. Right, hope that was okay. So we're still on reaction 2. Just to be aware that sometimes the questions can flip between reactions. So we're still on reaction 2, so we're okay with that, okay? So when reaction 2 is carried out under different conditions, a compound with a molecular formula C9H21N is produced. Okay, so now we've got to draw the skeletal formula. Right, a lot of information in this. So they'll do this quite a lot. Give you if they want you to find this unknown, they'll just give you the molecular formula of it, because it doesn't give you any hints into what you are kind of reacting together. So we need to, when we finish up, we need to make sure there are 9 carbons, 21 hydrogens, and 1 nitrogen in this, okay? So it's reaction 2 again, but this time it's under different conditions. So different conditions from when we looked at question 1. And it also wants it to be in skeletal form, okay? I think usually this is where my downfall would be, and forget doing it in skeletal formula. Right, wonderful. Okay, so a lot of things that could go a little bit wrong with this. We could get the wrong number of carbons, we could not know what the conditions are, and we might not be able to draw in skeletal. So a few little tricks in this one. So let's have a look at reaction 2. So we named reaction 2, it was nucleophilic substitution, and we had excess ammonia. And the point of having excess ammonia was to make sure we just formed that primary amine. Okay, we just wanted that primary amine. So it says it's under different conditions. Right, I'm assuming this time they'll have excess of the halogenalkane. Okay, so they've just changed around those conditions. Right, so what happens when we have excess halogenalkane? Right, this is where further substitution occurs. So I've got a bit of a space underneath, so I am going to go down and just go through some of the questions. So in our original mechanism, we had CH3, CH2, Br plus ammonia, and we made CH3, CH2, CH2, Br. Okay. Right. Yes, I do know there's other things that we do make in this reaction, but I just want to focus on these things because this is what it's kind of going to be all about. These kind of 3 things. Oh no, we don't make a Br. Sorry. NH2. There we go. Okay. So in the original reaction back in question 1, we had excess ammonia. So this ammonia would keep on reacting until all your halogenalkane had run out, okay? And that would result in this being the primary product. Other products can form, but that one would be the kind of the primary one. Right, so this time I've changed, it says other conditions, and we said this time that our halogenalkane is in excess. So what's going to happen with that then? So eventually, because the halogenalkane is in excess, eventually we're going to run out of ammonia. That ammonia is going to run out, and we'll still have some halogenalkane. So that halogenalkane can go on and react with something else that has a lone pair. What else has a lone pair? Oh, this amine that we actually made. So what happens when all the ammonia is gone? Right, okay. Still got some of this left over. This is going to get involved. Oh goodness, look how long it is. I'm going to run out of space at the moment, aren't I? Right, so what's going to happen? Same with what happened with the ammonia. One of your hydrogens on your nitrogen is going to be substituted for this long R group. So, right, so this time we're going to have CH3, CH2, CH2, NH, also attached to, where am I going to put this? Running out of space, aren't I? CH2, CH2, CH3. Right, so what else could happen? If this is in enough excess, we'll have another thing with a lone pair on, okay? So eventually if that thing is enough in excess, this stuff will run out. Bye-bye. And then our halogenalkane is going to pick up another one of our, what have we got here? We've got CH3, CH2, CH2. Oh God, squeaky. Twice, haven't we? Right, why have I drawn it like that? Because I've got 2 of these propyl groups and 1 hydrogen, so I can just draw it out like that. Right, this thing has a lone pair on it, so what's going to happen again? That hydrogen is going to go, And we can now have all 3 of those carbon chains on our nitrogen. Right, still got a low power on it. If this is still in excess, if we're still going, we could run out of that. And then this time, close that thing. Ooh, that big thing there. I think this freaks everyone out because it looks so big and scary. Okay, and then that can go on and react. And then this time there's no hydrogen to be lost, but the R group can sit on our nitrogen. Our nitrogen is using all its electrons to bond. It normally only likes 3 bonds. This time we've got 4, so we create that positive ion, that quaternary ammonium salt that we make. So that's what happens if we have excess of the halogenoalkane. There'll be lots of the halogenoalkane, and we would just keep substituting all those hydrogens on our nitrogen group for this alkyl chain, okay, eventually. So, right, I know I've gone off on a bit of a tangent here and I've gone probably a bit too far, but let's have a look what we're actually looking for. So, different conditions. If we had excess halogenoalkane, this is what would happen. We'd keep reacting and reacting and reacting. Right, so one of these products that I've made surely has 9 carbons, 21 hydrogens and 1 nitrogen. Right, well, they've all got 1 nitrogen. Right, which one has 9 carbons and 21 hydrogens? There you go. So there's 3 carbons in each chain, there's 7 hydrogens in each chain, and there is 3 chains on that nitrogen. So there we go, I figured out what my actual product is. Ooh. So now I'm just going to draw it out. So it's skeletal, so I've got a nitrogen in the middle, and that nitrogen is attached to 3 carbon chains, and each of those carbon chains has 3 carbons. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Looks like some sort of lightning drawing. But funky. Right, so let's have a count. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 9 carbons, I've got 1 nitrogen. If I wanted to count out all my hydrogens, I would have 21 hydrogens as well. And I've got it in a skeletal formula. So there you go. So in order to kind of do that, you have to have pretty much knowledge about what happens in further substitution. So it now says functional group including classification. So this is still an amine, okay, still an amine, it's got a nitrogen, things attached, but everything that's attached is a carbon chain, okay, so 3 carbon chains attached, so we've got a tertiary amine. If you wrote tertiary, that is fine, or if you just do the little 3 degrees thing, that is also fine. If you just put amine, it wouldn't work out. It does specifically say classification. So classification is the fact that it's tertiary, and the functional group is the fact that it's an amine group. Okay. So that's okay. So with further substitution, how do you kind of work it out? I always think it's a little bit backwards from what we learn in the nucleophilic substitution reactions. In nucleophilic substitution, each time you're pretty much just swapping bromine for that kind of ammonia group. Now you've got to kind of think that you're now basically swapping your hydrogens that are around nitrogen, those hydrogens and ammonia, for that kind of carbon chain. So this can happen with just a regular primary amine, secondary amine. Okay. If the amine or the ammonia is in excess, there would be just pretty much one substitution, and that one substitution, the product from that would be the major product. This would probably happen in a regular reaction as it is, but the major product would just be the one substitution. Whereas if we changed it and had the halogenoalkane in excess, we'd have these further substitutions. Okay, all the way down to quaternary ammonium salt. Great stuff, right. So yeah, I know that was a lot of conversation for 2 marks, wasn't it? But wanted to kind of make sure we went through it and we're happy with it. I don't think anyone's commented yet, so we're all good. Right, so question 2. An amide link is also formed when an acyl chloride reacts with a primary amine. Right, name and outline a mechanism for the reaction between CH3CH2 COCl and this amine. What have we got here? We've got ethanamine. There we go. And give the IUPAC name for the organic product. Right, brilliant. So I see amide link. An amide link is like that peptide link we've just spoken about in the DNA. You've got a C double bond O and then this NH on there. So this comes from when we react an acyl chloride with an amine. It's pretty much the same as the reaction between an acyl chloride and ammonia. It's just that we've got a carbon chain on our ammonia, not just 3 hydrogens. Cool. So let's draw out this kind of structure first. So I've got a C double bond O, Cl, and then I've got CH2, CH3 on there. Right, so if you're unsure what that is an acyl chloride. Acyl chlorides have got this carbon double bond O and a chlorine attached. So what actually happens here? So I'll come on to the name of the mechanism a bit later. Oh, a 6 marker, it must be a beast of a mechanism. Oh, we've got to do some naming, haven't we, as well? Right, so that acyl chloride is reacting with this amine. Right, so amine. Got a lone pair on the nitrogen. Right, we've got a nucleophile. We've got something that wants to donate its lone pairs. Right, what does that nucleophile want to donate its lone pairs to? Something positive, okay? This is the whole thing with mechanisms. You're always going to go from an area that's negative, either has a lone pair or has high electron density, to something that is positive. So let's have a look at this thing. My carbon's going to have a little delta plus, and my oxygen is going to have a little delta minus. Difference in electronegativity, so a delta minus on the Cl as well. So that lone pair on that nitrogen is going to be attracted to that slightly positive carbon. So I'm going to make sure that I start my curly arrow from a lone pair. Curly arrows must always start from a lone pair or a bond. Don't have them floating around, make it clear. Right, hello, I'm going to be attracted to this positive carbon. Right, what does that show? That shows that we are now making a bond between the nitrogen and the carbon, okay? That shows that lone pair and that nitrogen coming together with the carbon and forming a bond. Right, if that forms a bond with carbon, that means that we have too many bonds around carbon. Carbon only likes to bond with 4 things, so we're going to break a bond. Right, if this was nucleophilic substitution, the chlorine would be gone straight away. Right, the issue is we've got a double bond here, and one of those bonds is a pi bond, which is actually a little bit, well, it's not as strong as a sigma bond. So if you remember that stuff back in benzene, between pi bonds and sigma bonds, the pi bond breaks. You don't have to explain it, so don't worry if you're not too sure. Just basically know that one of those double bonds will break. Right, so my arrow starts from the bond, and the electrons in that bond are given to the oxygen. So the bond breaks, and the electrons that were in there are being given to the oxygen. Don't forget, when we draw these stick lines, it's a shared pair of electrons, so within that stick, there are electrons in there. and they need to go somewhere if the bond is broken. Right, so we'll have an intermediate now. So we've still got our carbon in the middle. Nothing happened between carbon and chlorine. Nothing happened between carbon and that alkyl chain. Sorry, it's part of my arrow. I don't draw these far enough over. Apologies. CH2, CH3. Okay. Right, nothing happened between those two. So they're the same as in our original structure. Right, problem is, here we go. Nitrogen attached. Right, nitrogen's now got 2 hydrogens, CH2, CH3. Right, nitrogen only likes to do 3 bonds, so at the moment its lone pair is being shared with the carbon. It's not happy about that. Feels a bit electron deficient, stealing my electrons. So it's got a little positive charge on it. Right, so what's happened to the oxygen? One of the bonds broke. So we've got this single bonded oxygen, and it was given a lone pair, so it has this negative kind of charge on it. Oxygen likes to bond to 2 things, so it's got electrons to spare. Right, so this is not our final product. This is unstable. It doesn't want to be like this, okay? So we now have to figure out a way to change this up. So we're going to form our bond again. So that lone pair on that oxygen is going to go and reform a bond. Now, random, you do say. Why would it break the bond to form it? So it broke it in the first place because the pi bond was weaker and it was easy to get rid of. Now it's got to this kind of intermediate stage. It realises it can kind of stable itself by forming that bond again and booting out that chlorine. Okay, so we are forming a double bond. If we form that double bond again, carbon will have too many things attached. So we're checking out chlorine. Why chlorine over that? So chlorine's kind of classed as a good leaving group. It leaves in our halogenoalkanes when we react it with a nucleophile. It's leaving here. Right, last arrow on this. Nitrogen's not happy, it's got this positive charge on it. So we're going to break a bond between the nitrogen and one of the hydrogens and give those electrons back to our nitrogen. Right, so what does that mean for our, oh gosh, we're over that space. So what have we got? Carbon in the middle still. It's now formed a double bond with oxygen again. It's still attached to the nitrogen. The nitrogen has 1 hydrogen left and this carbon chain with 2 carbons. And then over here we've got CH2, CH3. There's nothing changed with those. So there you go. One that people don't like. I don't understand why. I think it's quite a nice mechanism. Why is it not? So addition is a similar, nucleophilic addition is a similar reaction to this, but in nucleophilic addition, we just add something, okay? So in nucleophilic addition, we break the double bond between the carbon and the oxygen, and then either a hydrogen ion or a water molecule gets involved. With this, we are adding this amine, and then we are eliminating the chlorine. So we're using a nucleophile to it, so we've got nucleophilic addition because we're adding the amine, elimination because we are then taking out our chlorine. If you kind of look at it, it's similar to substitution. With substitution, you just have the nucleophile go in and then the halogen actually just leaves. This one's addition elimination because we are adding our nucleophile and then we are eliminating the halogenoalkane. Whereas substitution, it's just pretty much a straight swap. Right then, so we need to name this thing. Ooh, naming amides. Right, so I know it's an amide because I have this. Okay, it's pretty much this thing. So I know it's going to finish. Oh, do you know what? I'm just going to do it on the line below because I don't want to run out of space. So, amide. Right, so now I have to know what kind of an amide. So I'm going to count my carbons. in pretty much the amide chain. So the amide chain is the one with the C double bond O. So I've got 1, 2, 3. So 3 carbons. So I need to call it propanamide. Right, no E in this one because amide starts with an A. If we put an E in, that'd be 2 vowels together, wouldn't be correct, okay? So we've got propanamide. Right, so what else do we have to deal with? We have to look at this amine group over here. Ooh. Right, so it's got a hydrogen and it's got a carbon chain, so there's something else we need to add to it. So the carbon chain attached to the nitrogen has 2 carbons in it, so it is an ethyl group. Right, we need to make it clear that that ethyl group is attached to the nitrogen. Okay, we have to make it quite clear that the ethyl group is attached to the nitrogen, so I just need to put a capital N in front of that. The ethyl group could be attached to your the amide kind of chain, so we need to make sure it's clear that that ethyl group is attached to the nitrogen. So the N just in front of the ethyl means it's attached to the nitrogen in this case. Cool. Nice. I like that mechanism. I don't know why people get worried about it. Amines, when it comes to naming things, but you don't really... Naming amines doesn't come up that much because it's so ambiguous. There is so many different ways of naming amines. Amides are the one that they're going to name, if anything. So just be kind of aware of how to kind of name them. And if you've got any questions, Brenda's on the chat to kind of let you know. Okay, question 3. Right, brilliant. So this is kind of linking in with our acids and bases topic. And amines. So amines, ammonia, all that jazz, weak bases. Okay. So we've got amines. E, F, and G are weak bases. Explain the difference in base strength of the 3 amines and give the order of increasing strength. Right, lovely. So first thing I'd probably kind of want to talk about is what makes something, what changes the strength of an amine, well, as a base anyway. So bases are proton acceptors, aren't they? So they're trying to attract a H+ ion that's come from one of our acids. So it's all about the lone pair on our nitrogen. Okay, so it's all about the lone pair on our nitrogen and how available it is. So we put that down. So your strength of this depends on the availability of the lone pair. Right, so now we need to know what makes that lone pair either more available or less available. Right, so I'm going to focus on these two to start off with. Right, why? So in E, we've got an amine group attached to our benzene ring. Okay, that screams it out to me, okay? And we'll talk about why in a second. So our amine group is attached to a benzene ring. Right, reason why I'm talking about F is because here our amine group is attached to a carbon chain, to an alkyl chain. Okay? Right, reason why I'm leaving G out is because not only is it attached to a benzene ring, it's also attached to an alkyl chain. So you know what I mean? That's just a bit overcomplicated at the moment. I'm just going to stick with the definite ones in this question, okay? One that's on the benzene ring and one that is attached to an alkyl chain. Yes, there is a benzene ring there, but that NH2 group is far away, okay? Further away from it. So the benzene ring doesn't really affect that particular amine group because there's a whole carbon chain in the way. Right, so I'm going to talk about the one with the benzene one first. So I'm going to say that E has an amine group attached to a benzene ring. Right, why is that important? Why is that important? So it is pretty much because the lone pair is quite close to this ring of delocalized electrons. It's kind of close. Those delocalized electrons are all in the middle, having a little electron party, woo, spinning around benzene. This lone pair is like, oh, I want to join. So it kind of becomes part of the ring. It's close enough to go and join that delocalized party that's going on with all those electrons. So in E, our oh gosh, right now. So in E, our lone pair becomes delocalized into the ring. So what does that mean in terms of the base? So the lone pair is less available. So that lone pair is now part of the delocalized ring party. So it's got no time for any hydrogen ion kind of that is coming past. It's kind of just like, oh no, I'm having too much fun over here with my little delocalized friends. So it doesn't kind of get involved with, well, we'll get involved with the hydrogen ion, but it's less available to get involved. It's having too much fun in the delocalized ring. Okay, so in terms of F this time, so F has a nitrogen attached to the alkyl group. So it's on the end of a carbon chain. Right. What do alkyl groups like to do? Alkyl groups have that positive inductive effect. What is that? That is where electrons are kind of pushed towards its neighbouring atom. So in this case, the electrons in the alkyl group are pushed towards that nitrogen. Okay, so we can put that in. Alkyl chains have the positive inductive, have that positive inductive effect. So electrons are pushed towards nitrogen. Right, well, what does that mean for the lone pair? So if that alkyl group is pushing electrons towards that nitrogen, electrons are negative, the lone pair on the nitrogen is going to be kind of like forced away. Those electrons kind of repel, so that lone pair is kind of forced out, which makes that lone pair more available for a hydrogen ion. So on that last bit, lone pair is more available to attract H+ ions. So alkyl groups push electrons towards nitrogen and it forces out that lone pair a little bit, so it becomes more available for a hydrogen ion. If your nitrogen is attached to a benzene ring, that lone pair becomes falls into the delocalized ring and parties with the delocalized electrons, and it becomes less available. Right, what about the kind of one in between? It's just in between. Even though it's attached to a benzene ring, so we've got some form of delocalization, we've also got electrons being pushed towards the nitrogen. So it kind of makes that one a bit more available than E, but not as available as F. So G kind of sits in the middle. And actually with the mark scheme, you didn't have to talk about G, you just had to, when you put it in order, you just had to make sure that G was in the middle, because it had a bit of both in there. What they wanted you to say was that 1 mark for this, E next to the delocalized ring, that's mark 2. Less available, saying that it becomes less available, that's your mark 3. F next to an alkyl group, so that's your mark 4. Alkyl chain has a positive inductive effect, so it is more available. You actually didn't even have to say, oh no, you do have to say about the inductive effect, so that was your 5. Right, what was the last question then? Just putting them in order of increasing base strength. So you pretty much had to say that F was the strongest, then G, and then E, in that order, because it does say and give the order of increasing base strength. So that was your 6 mark. So you didn't really have to mention anything about G. You could say G was, it had an alkyl group, so it had electron density pushing towards it, lone pair more available than E, but you didn't really have to talk about G as such, to get the marks anyway. Yeah, as long as you were quite positive that you've got about strength of base depends on the availability of lone pair, and then talking about delocalizing to the ring, less available for the hydrogen ion, or having an alkyl group, you've got this more availability. Okay, so yeah, so I think that threw people that year that came out because of that G. People was trying to kind of like talk with it, but no, didn't really have to speak about it. Right, okay, again, something else that's going to start to crop up a bit more, these kind of synthesis steps. So we do have a bit of a pack on synthesis, but it's pretty much revision of your organic mechanisms. So all a synthesis is a way of starting from one product and getting to something that you actually want. And saying that it's a 3-step synthesis is because we start with something, make a little intermediate, that's step 1. Use that intermediate, make something else, that's step 2, and then finally use that to make our final product, so that's step 3. So 3 separate steps in order to make our end compound. So we have to have a look at this. So we've got amine F. Right, where's amine F? Right, so that is your, because it's on a different page, it's your benzene ring with the alkyl chain and then an NH2. So that's what we want to make. That is our product. That's going to be our end goal. I don't know whether I'd stick it at the bottom. Ooh, sorry, that's weak. But that's our end goal. So what are we starting with? Ooh. Methyl benzene. Ooh. Which is a benzene ring with a methyl group on. Nice. Right. With these, I now have to look at the difference between this thing and this thing. What's the difference between the two? So we've got an extra carbon in there and we've got an amine group. So there's a few things happening in there. Right, as soon as people see the benzene ring, they start going to the benzene pack and doing the electrophilic substitution. Right, electrophilic substitution only happens when you are attaching things to the benzene ring. Right, between here and up here, we aren't attaching anything to the benzene ring. We are just adding to that kind of carbon chain. So, lots of things to kind of think about. Right, sometimes I kind of work backwards with these. I think sometimes it's a little bit easy to work backwards. And I start to think how I make certain compounds. And the more you go through your mechanisms and your mechanisms of the week, the more you get familiar with what the different compounds form. So I can see there that I've got an amine group. So I think to myself, hang on a second, what makes an amine? Right, well, we can do nucleophilic substitution with a halogenalkane. So I'll have to do that at some point. But then something's flagging up to me because in here, I've got one carbon. Up here, I've got 2 carbons. Right, this is something that I always kind of say to my classes. If you are forming an amine where there's been an increase in the carbon chain, there must have been a nitrile involved. So if you can't remember what a nitrile is, it's this. So a nitrile group contains a carbon and a nitrogen. And so by adding a nitrile group, you increase the length of your carbon chain by 1 carbon. This is what's happened in this reaction. Our carbon chain has increased by 1 carbon. So I know that at some point, to make that little product over there, I will have had to have had a nitrile group in there. Right, how do you get from a nitrile group to a amine? Right, so what's different about here and here? I've just added a load of hydrogens. So this is a reduction reaction. It's not something we have a mechanism for. It's not something we have a mechanism for, and it's always kind of hidden at the bottom of your packs. So people always kind of forget that it exists. So, right, one thing to know then. So how to get from a nitrile to an amine? We add hydrogen. Okay, so hydrogen is something that we add. And we need a nickel catalyst. So this is something that kind of crops up. Hydrogen in a nickel catalyst also turns an alkene into an alkane. We can add hydrogens into that as well. So this is another way of, so hydrogen and nickel catalyst can kind of work in 2 ways. It turns our nitrile group into an amine, and it also changes an alkene into an alkane. There is another reduction one. It's where we got, remember we had the NO2 structure on our benzene ring, and then we formed an amine from that. So there are, I think there's 3 of them, where it's just a little reduction reaction, no mechanism, you just have to know the reagents and the conditions. So it's hydrogen with a nickel catalyst, which we'll kind of come on to in a little second, because I think I need to use those to answer the question. Right, so that will be my final step. And I knew that because I realised that my carbon chain is extended by 1 and it's got an amine group on. And I know from trying out lots of different versions of this question that a nitrile group will be able to do that. Right, next thing is, how the heck, so this must be the final step. So this is your step 3 that we'll kind of get in there. Right, so step 2 must be forming this thing. Right, so how do we form a nitrile? How do we form a nitrile? Oh gosh, I put too many hydrogens in there. Sorry guys. How do we form a nitrile? Back in your halogenalkanes pack. So the cyanide ion is a nucleophile, and it is a nucleophilic substitution reaction with a halogenalkane. Okay, so CH2, I'm going to do Cl just because I can. You could have used Br, that would be a problem. Right, so how do I go from this to this? I need a cyanide ion, and I get that from KCN. Do I have many? Do I need to be alcoholic and aqueous? So that is the aqueous and alcoholic as well. Okay. So there we go. That's what makes that. Right then, so that would be step 2. So obviously there's going to be a step 1 somewhere. Right, so that must mean that my methylbenzene has to go on and make this halogenylalkane. Oh goodness. Well, I need to add a chlorine to a alkane group. Right, alkanes only have one reaction and it involves those radicals. Again, when we get to the synthesis thing, people forget that that kind of exists. So I need to change that into that. And what do I need to do it? I need to do chlorine and I need some UV light. Some free radical substitution. So this might have been a bit tricky for you all because you don't really know which patch you need to be in. It's kind of hard to see the different steps, but when you get more happy with your mechanisms, it'll all kind of come to light a bit more. To be honest, I don't think I've answered the question actually properly here. I've just kind of gone through the little steps. So it suggests the structures for the 2 intermediate compounds. So in your answer, I'm just going to get rid of this. In your answer, the 2 intermediates, right, intermediate products are just things, oh, it just looks like a radical, it should be. Intermediate products are just products you make in the middle. So that's not one of my reactants, it's not one of my products that I want, it's not amine F or methylbenzene, so that's one of my intermediates. That is my other intermediate. Obviously, in your answers, you won't have all this little bit of extra information. I just wanted to show you guys what to do. So you will need to draw out those 2 compounds, your 2 intermediates. For each step, give reagents and conditions only. Equations and mechanisms are not required. So my equations there probably aren't required. So I could have just probably rubbed those out, but I need to have made sure I've given reagents and conditions. So this first one is free radical substitution. I've added a chlorine, so I needed chlorine. And for free radical substitution, I've needed UV light. So there we go. Those were marks for them. Well, I think it's 1 mark for, so it's a mark each for the intermediates and then a mark for the reagent and conditions. Right, so I get a mark for those 2. You don't get a mark if you've just put the nitrile ion. Sorry, not the nitrile, the cyanide ion, because if you've just put the cyanide ion, that's not a reagent, that is the nucleophile, and it has come from KCN. Okay? And then the last one, you get a mark for the hydrogen with the nickel catalyst as well. So even though I wrote all that out, it's only the things that I've ticked and then the things I've squared in blue that we actually needed on there. So hopefully that's okay. Brendan's asked any questions. No, that's all right then. Right. So I think this is the last set of questions, isn't it? Okie dokie. So compound C, wow, that's a beast of a compound, can be made from chloropropane in a 3-step synthesis. So here, I'm just going to point that out, even though you don't need to properly know this for this question. Look here. We start with chloropropane, and we've swapped it for that cyanide, and then the cyanide has formed this amine. So the chloropropane, that had 3 carbons, and this thing over here is 1, 2, 3, 4 carbons. So by using that cyanide, we've added the extra carbon and the nitrogen. So sorry, just kind of linking that in with the last question to kind of help you out. It's just a common one that kind of crops up every year. So compound C looks really scary, and it can be made from chloropropane in the 3-step synthesis below. Right, so it wants you to name compound A and compound C. Ooh, compound C looks mean. Right, compound A, let's just deal with that one because it's quite nice. So we've got a C triple bond N. So we've got a nitro, oh, I don't know why that's not on the board. So we've got a nitrion. I've got 1, 2, 3, 4 carbons. So I've got butane-nitrile. Remember, look with this one, I've got the E on there, the E, look at where the E is, I've got the E, because I've got two M's next to each other and we don't want that, okay? So, when it comes to like naming these things, if we're using the alkane name, if the next part of the name has another vowel that it starts with, you get rid of the E, but if it doesn't, if it has a consonant, you keep the E. Okay, so butane-nitrile, right, lovely, that's a mark, that's a nice easy mark. Right, this thing then, oh god. Right, so I see it's got a nitrogen and it's got a plus on it. That screams to me that quaternary ammonium salt, okay? Screams to me quaternary ammonium salt. And again, after you've kind of done a few things, it kind of gets in there. So the end of this name, right, it's got a bromide ion involved. So at the end of our name, ammonium bromide. Sorry. So ammonium bromide, because that's how, with the quaternary ammonium salts, that's how we kind of end it. It's an ammonium bromide. So, what about the rest of it? What do we have on that ammonium bromide? Well, we've got 3 of these groups, and I've got 1, squeaky, of this group. Right, so this group is an ethyl group, and this group, I've got 1, 2, 3, 4 carbons in. This is a butyl group. Right, so I need to put them in alphabetical order, don't I? So I've got butyl and then ethyl. But I've got 3 ethyls, so I've got tri-ethyl. Butyl triethyl ammonium bromide. We don't need to have any N's in because in an ammonium salt, everything is attached to the nitrogen, so we don't have to include the N's in there. We're just fine to have butyl triethyl ammonium bromide. Oh, that's a mouthful. That is a mouthful. Right, so for step 1, give reagent or reagents and conditions and name the mechanism. Balanced equation and mechanisms are not required. Excellent, so I just need reagents, conditions and the name of the mechanism. Right, for step 1. So remember, this is another example of a 3-step synthesis because it's 3 steps to go from what we start with to what we want at the end. So, I need reagents and conditions. We've just done this, haven't we? Lovely. So, chloropropane. If you're not sure what it looks like, 3 carbons and a chlorine. I'll add the hydrogen just so everyone's happy. It's not like I'm drawing it out. So. Right, so what's changing? I'm swapping chlorine for this. Cool. So, again, nucleophilic substitution. Not addition elimination because I've not got any double bond oxygens in. Nucleophilic substitution. Oh goodness. Oh goodness, it's terrible. The balls are standing for me. Substitution. Okay, so nucleophilic substitution. Right, and I want KCN as my reagent, not just the cyanide ion, I want KCN, that is my full reagent, okay? Right, and then alcoholic and aqueous, to be honest, the main condition is the fact that it's alcohol. Can't spell it either. Alcoholic. Or ethanolic. If you put ethanolic, that's absolutely fine, or alcoholic, same thing, same difference. Okay, so alcoholic. So nucleophilic substitution, KCN, and it needs to be alcoholic. Those are your 3 marks. Didn't even have to do a mechanism. Good effort. Right, step 2. Right, I'm going to have to go back. What's happening in step 2? Oh, look at that green. So step 2, we're changing that. Yeah. We're changing that cyanide to all that. So we're adding the hydrogens again. Okay, see, look, it does crop up a lot, does that one? So give the reagent or reagents and name the type of reaction. Balanced equations and mechanisms using curly arrows are not required. So we need to put that in. So all I'm going to say is we need some hydrogen, because we're adding hydrogen, and we need our nickel catalyst again. Okay. What else did it want? Oh no, it's 2 marks. Reagent mechanism. Oh, type of reaction. Right. It is a reduction reaction. Okay, reduction reaction. Ta-da. Right, are we down to our final questions now? I think we're doing final 2 now. We're on the home straight, guys. Look at all this space though for just that. This is where you don't need to be freaked out by the amount of space you're kind of given sometimes. They just do it to be aesthetically pleasing, but that's just madness. You'll need 3 points. Right, okay, so for step 3, give a reagent, give a condition and name the mechanism. Okay, balanced equation and curly arrows not required. So step 3, what's happening? Oh god, I've just scribbled all over this, haven't I? Right, okay. Okay, so let me just get rid of all of this, so we can actually full on see what's happening. Right, so we've got this big scary molecule. Sorry, I meant to see your big scary molecule. But we've got this big scary molecule. Right, how does it even relate to B? Right, I'm going to have to look really, really hard, but then I can see it. 4 carbons and a nitrogen. It is there, okay? It is there. So what has changed? Right, well, we've got a bromine for 1. That might give us a bit of a hint. We've added this ethyl group. Well, not it. We've got 3 of them, haven't we? We named it. We looked at it. We named this thing. We can see that there are 3 ethyl groups involved. Okay, so we've got 3 ethyl groups. So what has changed? We have added 3 of those. Right, this takes us back to that mechanism at the beginning, where we had our ammonia, our amines, and they were acting with a halogenoalkane. Which halogenoalkane? Well, because you've got a bromide ion here, I'm guessing that must mean that it involves that. So remember what I said with this, when you do further substitutions with a nucleophile substitution, each one of those hydrogens, yeah, has been swapped for this R group. And then at the end, that lone pair on nitrogen has continued to kind of react and form that quaternary ammonium salt again. Right, so this is involved in step 3. So, what do I need to put? Reagents. So, one of my reagents, did I do too many carbons on that little one? Why have I done 3 carbons? You're all probably shouting at me going, there's too many carbons there, Kim. There is. And I realised that when I looked at it. Always good to check. Sorry, 3 times those ethyl ones. Apologies about that. Get carried away with my carbons, there's so many of them. Right, so I need that halogenoalkane. Right, I need a condition for it. And it is that the halogenoalkane is in excess. In order for that amine to keep on reacting and make something new, make another amine and then keep that reacting, we need our halogenoalkane in excess. Okay? So the halogenoalkane is in excess. If we wanted it to stop after 1 substitution, we have the amine in excess. Right, and it wants a mechanism. Right. Just a bog standard nucleophilic substitution. And again, literally, those are your 3 marks. And look at all that space. Psych things out in exams, I tell you. Right, so last one, 2 marks. Identify one organic impurity in the product of step 3 and give a reason for its formation. Right, only one. There's a few options. So what could happen? Pretty much the reaction could be incomplete. You could get to a stage where you've got incomplete. And remember, this thing, yeah, reacts and then forms another amide. And then that reacts and forms another amide until we get to this point. There's lots of substitutions involved. So we could have our, we could have B, and it might have only done one substitution. So if we just get rid of one of the hydrogens, we could have had something that has CH3. I need to remember to do the right number of carbons this time. It was a bromine, wasn't it? 1, 2, 3, 4. Yeah, 1, 2, 3, 4. So only one of our hydrogens could be substituted for that ethyl group from this thing up here. Or could still have our amine. And maybe two of them might have been substituted. Okay, rather than it forming the ion. And either of those could be formed because of an incomplete reaction. So you didn't have to get both of them, just one of them. So because it's a further substitution reaction, okay, this will have been actually probably made first, and then that would then followed on and reacted and formed that, and then this would have formed, and you would have ended up with the final product. So this is kind of what you finally get. So those would be impurities. When it is organic impurity, okay, it has to be something with like the carbons in and stuff, so just to kind of make you aware. And why would it happen in complete reaction? Right, I hope that was useful for you all. Oh, there's not been much on the chat. I'm hoping everyone could have can use the actual chat facility. But yeah, so hopefully that was useful. If you want to stay on or have any questions, let me know. You can just stay on and just stay behind, and I'm happy to answer. But this will be available as a video as well at the end. So on Moodle. So thanks, guys. Stop recording.
Thanks, Kim.